So what we're going to talk about in this last section is how we can deal with particularly things pertaining to a circle and how they relate to specific topics in physics. And what we're going to talk about is how a point can relate to how it relates to going around a circle. And this idea of velocity is going to be brought up a lot, and basically what velocity is just speed with direction. But let's suppose we have this point here on this circle, and we wanted to describe, keeps disappearing on me, but if we have a point on the circle, we can describe how fast this point is going around this circle, because velocity is described as distance traveled over time. Well, if we're talking about a distance and a point going around a circle, all we need is, for this linear velocity, is a specific distance over time. Well, that distance is going to be arc length. To find velocity, again, it's distance over time, but on a circle, it's the arc length that the point goes. It's the distance around the circle that it's going. It's the arc length. Okay, well, the arc length is going to be the total length, but the point from start to finish, that total distance is going to be arc length. So to find linear velocity, which we were going to just call v, is going to be that arc length over time, or r times theta over time. So if we have a specific angle, we can also talk about how fast that angle is changing, because as this point is going around, this angle is constantly changing as well. So this central angle, I know it's hard to see without seeing it in motion, but if we start with a point here and then the point keeps moving around the circle, this angle is constantly spinning. So this angle is constantly changing as well. So we're talking about how an angle is changing over time. So it's the distance the angle is traveling over time. Now the symbol for this is a Greek letter, and it's a Greek letter, and I believe it's a omega. And the formula for this is the angle distance traveled over time. Okay, now what you might see is that there is a distance, there's a correlation, and we'll get to that in a second. But suppose you ride a Ferris wheel at the amusement park. If the wheel is spinning at an angular velocity of pi over 15 radians per second, so that's how fast that angle is changing. So it's going around at pi over 15 radians per second. The question is, how many degrees have you rotated after 1 minute? Well, we first have to figure out a couple things here. If it's pi over 15 radians per second, we need to change how many degrees there are, because in 180 degrees there's pi radians. So I can use that unit conversion, and there are 60 seconds in 1 minute. So I can make these unit conversions to figure out how many degrees you've rotated after 1 minute. So what I'm left with is 60 times 180 over 15. So for A, what I'm left with is 720 degrees. How many seconds does it take to make 2 revolutions? Well, Oddly enough, we already determined that based on the fact that 720 is equal to 2 revolutions. But let's change this. Let's change it to 10.5. So let's make 10.5 revolutions. So if we know that 2 pi is 1 revolution, we're going to times it by 10.5. And we get 21 pi. So that's how far we want to go. Okay? And we know that this is the distance that we want to travel. This is our arc length. Okay? That's our arc length. And we know that this is the arc length, or our angle that we're going to be using. So this is our angle. We know our angular velocity is pi over 15. So now we just have to figure out how long it takes for that to equal 21. So if we cross multiply and divide, we get 21 pi times 15 divided by pi. So I get those 2 pi's to get rid of, so I have 21 times 15. So 21 times 15, I get what appears to be 315 seconds. Now I did this kind of a roundabout way because I let this be my angle, and my angular velocity is how fast my angle was going. Now, there is a couple of ways that you can do this a little bit differently, because of the fact that we have these two formulas, and I'm going to change this one with r theta over t for linear velocity, and the fact that we have this formula for angular velocity which has theta over t already in it. So these two things are exactly the same. So I can replace this right here with what it's equal to, which is angular velocity. So I have this grand formula which relates linear velocity and angular velocity, and the only thing that relates them is the radius. Okay, so if you have angular velocity and a radius, you can create a formula for linear velocity, and there it is. So let's take a look at this one here. It says, suppose a dog is on a 12-meter leash in the backyard and he's running at an angular velocity of 2 pi over 3 radians per second. What's the dog's linear velocity? Well, with a radius of 12 and a angular velocity of 2 pi over 3, if I multiply that together, I get 24 pi over 3, or 8 pi. Now you might say, what does that mean? Well, that means the linear velocity is that the dog is running at 8 pi meters per second. So that dog is running around that leash pretty fast. Okay, now these two I will talk about in class, but again, the idea is that if we're talking about a formula for arc length and we divide that by time, we get to a point that talks about velocity. And velocity is going to be how fast a point is traveling around an arc, particularly linearly. Now, if we talk about how fast this angle changes, because this angle is going to change as this point is changing, then we talk about angular velocity. And we're talking about how fast an angle is changing over time. Now, because these two things are related, because we have an angle and time, we can relate the two things in one equation based on just the radius. So linear velocity and angular velocity are both related based on the radius. And that's the outcome that we needed to get from today.